Okay, scientific notation. Scientific notation is a number written of the form c times 10 to the nth, where 1 is less than or equal to c, less than 10, and n is an integer. So that's a lot of words, but here's what it means. If I give you the value 725 million, so that's a lot. Maybe I was saying how many drops of water are going to fit in a bucket? 725 million drops of water. Something like that, and I had to measure. Well, maybe if I'm calculating things out, I might not want to work with a number so large. So we have a different form that's going to show us the magnitude of it. It's going to show us really how big this is, but still hold true to what the answer is. So the first thing we have to do is find out what this c value is. And it tells us c has to be between 1 and 10. It can be equal to 1, but it has to be less than 10. So to do that, if I put a decimal point right there, I get 7.25. So really my c value in this case is 7.25. Now I have to continue the scientific notation. It says times 10 to the, and I need an exponent to represent how many place values I need. 10, every time you multiply by 10, you're really just moving the place value one more to the right or to the left. You're adding one more, depending on which way you're looking at it, but you keep adding one more place value. So to get from the original decimal point to where we placed it in, we're going to go 1, 2, 3, 4, 5, 6, 7, 8. 8 places, so my answer is 7.25 times 10 to the 8th. Okay? Now if I had another value, maybe it was something that was between 0 and 1, it was a decimal, 0.0000934. I need to first get my c value, which is going to be right here. So c is equal to 9.34 because it has to be greater than or equal to 1, less than 10. And now I have to see how many places I needed to go to get my decimal point here. So for my original, I go 1, 2, 3, 4, 5. So it's 10 to the 5th. But we aren't done yet because this here is a decimal answer. So when you have a decimal answer, your exponent has to be a negative. Okay, because it's a small, so this is a small number. The closer it gets to 0, the smaller and smaller and smaller it is. Maybe there's a microorganism that's 0.0000934, I don't know, centimeters long. That's super tiny. So we have to represent it with a negative exponent. If you leave it positive, positive represents a large number, massive, into the millions and zillions. So just remember, negative if you have a decimal. All right, the retina is a layer of the eyeball that contains rods and cones. Rods and cones are cells that absorb light and change it to electric signals that are sent to the brain. The human retina is 0.00012 meters thick and contains about 120 million rods and about 6 million cones. I think eyes, this is incredible that our eyes can have this much in them, all of our cells and everything that the body's made up with. We want to take this number, the number of rods in the retina, and write it in scientific notation. 120 million. So the first thing I need to do is find my c value, which is going to go right here. So it's 1.2. And it's always going to be times 10, not anything else. And we write our times here. This is the only time we're going to actually use an x to represent times. You don't want to put a dot. You want to use the x. It's just part of the notation. So we want to see how many place values it took to get there. 1, 2, 3, 4, 5, 6, 7, 8. 1.2 times 10 to the 8th. That's our answer. Letter B, the thickness of the human retina is 0.00012 meter thick, which is super small. Write this in scientific notation. So my decimal point is going to go between the 1 and the 2 because I have to have c, this is my c value, be between 1 and 10. And I have to find out how many decimal places, so it's 1, 2, 3, 4. But I see that I have a decimal, so my answer is negative because that represents a small number. Okay, so the reason scientific notation is used is because we're working with very small numbers or very large numbers. And if you were calculating something, maybe somebody was measuring the strength of a beam on a bridge. When they measure something that's into the trillions or gazillions, then you're going to have, there's a room for error. Like if you have a number that is like this. 3, 4, 5, 1, 2, 7, 9, 3, 8. And I just keep going. Chances are, if I'm actually measuring this in real life, that I'm not going to make it that accurate. Usually these are going to be zeros. And so rather than write all of them, we use scientific notation to save us some some room. So let's take this. We want to write this number in scientific notation. It's already large, so our first part is to put the decimal place in, 4.1, and then see how many places. 1, 2, 3, 10 to the third. This one, decimal place goes here, so it's 6.7, and I go 1, 2, 3, 4, 5, but it's a decimal, so it's a -5. Here we put our decimal, 3.46. times 10 to the 1, 2, 3, 4, 5, 6, 7. 10 to the 7th. And then we're going to do 1.45. If you're noticing, the pattern is that the decimal point always goes after the first actual number that's not 0. So 1.45 times 10 to the 1, 2, 3, 4, 5. And because it's a decimal, it's a negative. Represent a small number. Write these numbers in standard form, so we're going to go the other way. We're going to start with our number, 1.85, and we know that times 10 it's a positive exponent, so it's going to be a big number. So I'm going to go 1, 2, 3, 4, 5, 6, and just fill in these places with zeros. So my answer is 1,850,000, which represents an exponent that's positive, represents a big number, so we did it right. 7.89, we're going to have 5 spaces. 1, 2, 3, 4, 5. Fill in my 3 zeros. 789,000. Here we have 3.29 times 10 to the -4th. So I write my number down, and here we have a negative exponent. So in the end, our answer has to be a decimal because negative exponents imply decimals. So I'm going to go to the left. 1, 2, 3, 4. Put my decimal. And I end up with a small number like we know negative exponents imply. 4.57 times 10 to the -3rd. So I'm going to go to the left, 1, 2, 3, and I get 0.00457. So if we try these two, these ones down here, same thing, we're writing these in standard form. So 7.1, and I look at my decimal, it's positive, so I'm going to have a big number. So I go 4 spaces to the right, 1, 2, 3, 4. If you really just think about what they're asking, it's going to be a lot easier to figure out which direction you go. 1.93 times 10 to the -3rd. So it's a decimal because it's a negative exponent. So the only way to make a decimal is to go to the left. 1, 2, 3. So this one's 0.00193. Here we have 0.3641 times 10 to the -6. So we're going to go to the left. 1, 2, 3, 4, 5, 6. And fill in all of those zeros. And lastly, we have 5.59 times 10 to the 8th. Oops, I don't need to rewrite the problem. 5.59, I'm going to move it. It's a positive exponent, so my answer is large in the end. 1, 2, 3, 4, 5, 6, 7, 8. There are little ways of remembering which way to go, which way to turn, when to go left, when to go right. But again, if you just think about what your number should be in the end, that's going to help you figure out the direction to go. To compare numbers written in scientific notation, that's what we're going to do here. We want to compare and order these numbers, all 3 of them. Put them in from least to greatest. So what we're going to first do is compare the orders of 10, then the decimals. So right here it says write each number in scientific notation if necessary. Well, the first one is, so we're good. The second one would be 3.8 times 10 to the 6th, and the last one is already in scientific notation. Part 2, order the numbers with different powers of 10. These powers of 10 represent how many place values it has. So obviously the smallest one is the one that has to the 5th, so 4.2 times 10 to the 5th. And then we know that these come next. We don't know what order these are in, so they're kind of just hanging out there. Then we order the numbers with the same powers of 10. So now we can look at the decimals, 3.9, 3.8. Well, 3.8 is smaller, so that's going to go next. So we have our 4.2 from before. We have our 3.8 now, and then the last one's 3.9. Lastly, write the original numbers in order from least to greatest. So originally, 3.9 times 10 to the 6th was 3.9 times 10 to the 6th. So we leave that one the way it is. 3.308,000, that would be this one, 800,000, and then the 4.2 times 10 to the 5th is good the way it is. Thanks, guys.